Hello, welcome to this short video where I will talking about a polymer technology topic, the polymers for 3D printing. Well, printing techniques was introduced during the 80s to serve the highly specialized needs of model making and rapid prototyping. Additive manufacturing, alias 3D printing, has emerged as a versatile technology platform for computer-assisted design and rapid manufacturing. AM allows the production of customized parts from metals, ceramics, and polymers without the need for molds or machining typical for conventional formative and subtractive fabrication. Today, 3D printers are available for less than $500, enabling desktop fabrication of 3D objects even at home. In the same way that the development of digital 2D printing together with desktop publishing has revolutionized communication and information technology, the development of AM technologies in conjunction with the Internet of Things has the potential to revolutionize computer-guided fabrication of both complex objects and multifunctional material systems. Whereas conventional fabrication is governed by processing constraints related to industrial mass production, AM is inherently agile, enabling faster turnaround, design and manufacturing of customized objects tailored to meet the demands of individuals and specific applications. The terms additive manufacturing, rapid prototyping, layer manufacturing, solid freedom fabrication, 3D fabbing, and 3D printing are used more or less synonymously. While additive manufacturing is preferred by most engineers, the term 3D printing is far more common, particularly in the popular media. In this sense, the terms additive manufacturing or AM and 3D printing are both used to describe the same general manufacturing principle. In this example, the coffee mug is not very complex. It provides a convenient object to demonstrate the concepts of AM. In the first step, CAD is used to create a virtual object, which is then digitally sliced. Objects with overhanging positions are designed with temporary support structures to prevent collapse during the build process. The coordinates of the virtual object and digital slices are then used to steer the motors, which control the position of the building device or the 3D disperser orifice respectively. For practical purposes, this type of computer-aided manufacturing is normally performed layer by layer, with typical layer thickness ranging from 15 to 500 micrometers. When the layer thickness is below to 50 micrometers, the naked eye will in most cases not be able to recognize the stair steps associated with a layer manufacturing approach. For thicker layers or in demanding applications, post-processing may be used to remove support structures or to improve surface properties. As compared the conventional polymer processing by formative techniques like injection molding and subtractive techniques like CNC machining, AM is slower but enables CAD-guided fabrication of multifunctional material systems with complex shapes and functionalities including biosystems. With the development of easy-to-use systems exhibiting sufficiently fast build speeds and decreasing system prices, AM has moved from the arena of niche manufacturing processes into the spotlight of a much larger audience. Despite the significant progress that has been achieved in recent years, there are still a number of challenges that need to be tackled to establish AM as a manufacturing tool on a large scale. Many of these challenges are related to the insufficient material properties of the currently used build materials. With a focus on primary materials, in this video I will describe the different AM processes that use polymers along with the technical requirements of the utilized materials. Critical points which currently limit the further use of AM in manufacturing will be pointed out, and possible strategies for overcoming these issues will be discussed. Technology defined a number of terms to distinguish additive manufacturing technologies from their formative and subtractive competitors and to classify different additive manufacturing processes. We aim to follow this nomenclature in the course of this video. Well, the first is material extrusion. Material extrusion is an additive manufacturing process in which material is selectively dispensed through a nozzle. Fused deposition modeling, fused filament fabrication, 3D dispensing, and 3D bioploting fall in this category. Material jetting is an additive manufacturing process in which droplets of build material are selectively deposited. System based on inkjet printing fall in this category. Binder jetting is an additive manufacturing process in which a liquid agent is selectively deposited to fuse powder materials. Here I'll show you the sheet lamination. The sheet lamination is an additive manufacturing process in which sheets of materials are bonded together to form an object. The bath photopolymerization is an additive manufacturing process in which liquid polymer in a bath is selectively cured by light activity polymerization. Many of the litho-rapid based AM approaches can be grouped in this category. For example, multiphoton polymerization, digital light processing, and stereolithography are examples of bath photopolymerization. Powder bed fusion is an additive manufacturing process in which thermal energy selectively fuses regions of a powder bed. Selective laser sintering from 3D systems and laser sintering from EOS, both of which are abbreviated as SLS, and electron beam machining (EBM) fall in this category. These processes are used for metals as well as polymers. Finally, direct energy deposition. Direct energy deposition is an additive manufacturing process in which focused thermal energy, for example plasma, laser, are used to fuse materials by melting as they are being deposited. This process is currently only used for metals. The scientific and technological impact of additive manufacturing has steadily increased since the first commercial instruments were introduced in the late 80s. Here we could see the trend graphically by tracing the yearly number of scientific publications and patents from 1985 to 2016 using the terms additive manufacturing and rapid prototyping. Whereas interest in additive manufacturing has grown steadily for the last 25 years, the comparative younger field of bioprinting has witnessed a comparatively impressive increase in patents and publications within the past decade. Well guys, this was all of this video. In the next video, I hope to share you more about the additive manufacturing. Don't forget to share this video and subscribe to my channel.